Hello and welcome to this edition of the Telescope Makers Workshop. My name is Francis O'Reilly and I'll be guiding you through today's program. As you'll recall from several years ago, I've made a number of videos in which I detailed various processes used in the making of telescopes. Most recently, I've completed a 12.5-inch f7 telescope. The telescope itself is over my left shoulder. It's a very good telescope. The mirror came out really well. I brought it to Stellafane in 2011, and the 12.5-inch optic was awarded Best Optic in the over 12.5-inch category. Now, there weren't many optics showing, but I did a good job, and I'm very proud of the mirror. I'm very proud of the telescope, and I'm grateful to the help of my friends Alan Hall and Dave Grosky, and for helping me collimate it, and particularly to Dick Parker, who helped me make the telescope mirror, who guided me through the figuring of this particular mirror. Dick, you did a great job for me. Thank you very much. The telescope was mounted on an equatorial mount. It wasn't just any equatorial mount. It was a type used in the olden days. The equatorial mount was a pipe mount. It was made from plumbing fittings. Much to my surprise, it was pretty expensive to put it together. I would probably have close to $1,000 worth of fittings and machine work involved in making the mount. However, it's a very sturdy mount, and I'm at roughly 42 degrees north latitude, so it's set for 45. It tracks pretty darn well manually. I really don't have to move it very much in declination to keep it tracking on the polar axis, and that's a very major thing. I do not have a clock drive on it. There's no sidereal drive whatsoever, so it tracks manually, but it works well. Is it a big, clunky, ugly thing? Absolutely it is. But does it get the job done? It sure does. I want to talk to you today a little bit about the projects that I'm working on now. I've got two major projects that are going on right now. One I'm doing with a friend up in Connecticut, Al Hall. We're working in his machine shop, and I'm making a 8-inch f20 Cassegrain. The primary is from a Cassegrain from a mirror that I originally started some years ago. When I first got back into telescope making, I purchased a piece of glass at Stellafane, sent it out to Newport Glass to have a curve put into it, and I wanted it to be an f8, an 8-inch f8, because I like the longer focal lengths for the type of observing I do. But I got my numbers confused. I was tired. I put in an order, instead of for an f8, I put in an order for a radius of 64 inches, where I really wanted a radius of 128 inches. So I got a very fast mirror. Got it back, grounded, polished it out, came out pretty spherical, and I realized, you know what, I've got an f4 here. But that wasn't the end of the world, because okay, a wide field telescope would be great. Well, I've got the wide field telescope now, and what do I do with it? Well, it's a 200 millimeter blank, not an 8-inch blank. So it doesn't fit in any of the standard mounts. I could shim it, but I didn't want to do that. I brought it over to Al Hall's house, and Al and I talked about it. He said, why don't you make a Cassegrain? Ended up, Al talked me smooth into it. He pulled me over onto his computer. He's got a program called SolidWorks, which is a mechanical engineer design program. He's a mechanical engineer. Before you knew it, we had a mount, not a mount, but a mirror cell designed for a Cassegrain, a focuser designed for a Cassegrain. I'm out buying metal on eBay because he's got machine tools in his basement. Next thing you know, we're making a backplate, and then we're working on a focuser now. I've got the tube from Hastings Pipe, and eventually we'll also make an equatorial mount. So that Richfield telescope suddenly became a classical Cassegrain. And by the way, I bought the glass from Newport Glass for the secondary. They did put in a rough curve for me to a very exacting specification, 15.748 inches of radius, and they made not only the mirror, but they also made a tool for it out of plate glass, and the whole thing, the mirror and the tool, cost about $90 for a 47 millimeter secondary. I put a hole in the primary. I did that with a diamond tipped hole saw, the kind you buy from these Taiwan companies on eBay, and that's working out pretty well. I'm looking forward to figuring the 8-inch very fast mirror. It's a challenging curve, but it's not the end of the world. I'm really not intimidated by fast curves anymore. I've made so many mirrors. For a new mirror maker, maybe an f4 is a little bit much, but it just doesn't trouble me. The other project I'm working on is a 12.5-inch Stevic Pawl, and that's a 4-mirror system, a quaternary system. I've got the primary at a 12.5-inch f12, which is a huge, huge focal length. I look at the telescope, I get scared when I put it on a test bench because I know that I'm looking at a 12.5-inch focal length. The entire telescope is going to be close to 13 and a half feet long, and that's really long. In any event, that has a parabolic primary, and of course, as you know, the difference between a parabola and a sphere at f12 isn't much. So it's not going to take too much to get that figured where it needs to be, although a long focus mirror can be as challenging as a short focus mirror, trust me when I tell you. The secondary mirror is a convex mirror, and that's a convex mirror that is of a radius of 4/10 the radius of the primary in this particular case, and it's offset because this is an unobstructed telescope. So I've got a 150-inch 12.5-inch mirror that's 150-inch radius, a focal length rather, 300-inch radius. I've got a secondary, a 6-inch convex secondary, and that's got a radius of negative 60 inches, so it's a negative f10 mirror. The tertiary, and it's a sphere by the way, and we make that and test that with use of a test plate, which would be a concave mirror of the same focal length, and we test it under interferometry, looking for fringes. The tertiary mirror is a concave, spherical concave f7.5, and that curve should match pretty closely the secondary curve. They should be mating curves, except that the secondary is 6-inch and the primary is 8-inch. And we'll check that both through radius measurements and also through interferometry to make sure that we have the proper fringes and make sure the fringes look right. The quaternary mirror is simply a diagonal mirror that will shoot the light out the side of the telescope. And the intent is to balance this telescope so that the light comes out the trunnion in the mount and we can have something somewhat akin to a Naismith focus. Now the intent is to use this telescope both for planetary observing, near space observing, and also I'm going to give a shot at spectroscopy. And I have started to make a spectrometer. It's going to be a Czerny Turner spectrometer. I've already made the collimating mirror for that, and I've got a pretty interesting grating that was apparently at one time used by NASA to find the hole in the ozone layer. So I guess that's Al Gore's favorite grating. And I'm looking forward to getting this entire telescope made and put together, and hopefully, I don't think I'm going to be able to take this one to Stellafane, but I should be able to mount it in New Mexico on my property and have an observatory there, and as I retire, basically change from a day dweller to a night dweller and sleep during the day and do my astronomy at night. In addition to that, I guess I've been truly honored. I'm now a member of the Springfield Telescope Makers, and I have 2 dogs, Jack and Bailey, as you can hear. And Jack is a little bit curious what's outside, and Bailey is also looking out the window. So with that, I'll say good night and adieu. Francis Riley from Brewster, New York. Have a great evening.